Now we're going to have a nice change of pace and only do one problem for an example set. And we're going to say, okay, I've got negative 1 to the n plus 1 times n over 2 to the n. And I want to approximate the sum. Okay, so I kind of already said, okay, well, I know it's going to be convergent because I'm approximating the sum. And what you'd find is if you went all the way through this is an alternating series, and you can approximate it. You can even do some interesting things by showing it's absolutely convergent because it's going to be less than a certain geometric series and blah, blah, blah. There's a lot of really neat analytical things you can do here, but we're not doing any of that. We're going to assume that it is convergent because I know it's convergent, so trust me. And we're going to use the first 4 terms to approximate the sum of the series. And then we're going to determine the error on that approximation to kind of get a bound for what the true value has to be within. So by looking at this, I need to get the first 4 terms. So I need to get a1, which is negative 1 to the 1 plus 1, 1 over 2 to the 1. So negative 1 squared is just, that's 1, so this is 1/2. So a2 is negative 1 times 2, 2 squared. So this becomes negative 1, 2 over 2 squared. It's actually negative 1/2. That's kind of interesting, right? So that's actually going to cancel out. Third term, negative 1 to the 3 plus 1 times 3 over 2 to the third. So that becomes negative 1 to the 4th. That becomes just 1. So I now have 3 over 8, and a to the 4th, negative 1 to 4 plus 1 times 4 over 2 to the 4th. So this becomes negative 1/4. So then what I have here is I have S1 is 1/2, S2 is actually 0, S3 is 3/8, and S4 is 1/8. So S4 is 1/8. That is our current city. You know, by adding all these up, this plus that is 0, plus that's 3/8, plus that is 1/8. So that is our approximation. But I want to know my error. Well, the remainder, or error, has an upper bound of the n plus 1th term. So if we did 4 terms, we can get the 5th term, and that will. So I kind of cheated here because I said A1 through A4, when really with alternating series, you actually, the A is the term without the negative. But the problem is then I would have had to have like pulled it in. It would have been kind of ugly. So I'm kind of cheating and I'm calling AN this whole thing. And the reason why I'm mentioning that is because the theory also doesn't have an absolute value here. It just has AN because it's assumed AN is positive. But in this case I didn't. In this case I kind of sucked in the negative 1. So I have to write it like this. It's a little messier, but I thought the notation would be cleaner and less disgusting for you. So hey, pick your poison, right? So that means that the error is, so I need to get the 5th term because we only have the 4th term here. So I need the absolute value of the 5th term. Well, the 5th term so that negative, that's going to go away. I have a 5 on top over 32. So that tells me that my final approximation is within 5/30 seconds, which is kind of funny because it's actually larger than this number. It tells me my approximation is pretty terrible right now. We'd have to generate several more terms to get it to converge to something meaningful. So since the error is within 5/30 seconds, my error, or my what I'm going to call is convergence range. Sometimes it's like a radius of convergence or whatever, is So you know that the error is 5/32, but you actually don't know if the error is on this side or that side. So what you do is you take the value you have, take this, and you say, well, it can only go out this far, or out this far. So it just depends on which way you're going. So in this particular case, that's negative 132 up to 932. So the actual result sum of this has to be in this range. So I'm sure you could take this, and there's probably a neat analytical way for this particular series to find the actual sum, but it's going to be within this, and it's probably going to be a lot tighter than that, in fact.